Okay, is it visible, sir?
Yes.
Okay. So good afternoon, everyone. This is Nilanjan. I am going to discuss some recent developments on what we now call as the Bohr phenomenon. So the origin of the Bohr phenomenon, it basically lies in a result that was discovered in 1914 by the famous Danish mathematician Harald Bohr. So his main aim was to consider the problem of absolute convergence of ordinary D-state series. So that D-state series, I mean, that roots from this famous Riemann zeta function, which is all of us know that given by sigma s equals summation n1 to infinity 1 by n power s, also can be written as this product involving prime numbers. So generalizing this, an ordinary Dirichlet series is precisely a series of the form sum over n1 to infinity an by n power s, while n's are the coefficients in complex plane and s is a variable. So the problem Bohr originally considered was to determine the width of the largest possible strip in the complex plane on which this ordinary Dirichlet series D will converge uniformly, but not necessarily absolutely. So what Bohr did, he could only prove that the width of the strip that is less or equal to half. What he used a trick that he factored this n in terms of primes p1, p2, pk and replaced each prime by a complex variable z1, z2. So he got, in place of this Dirichlet series, power series in infinitely many variables z1, z2 and so on, while each term is a product of finitely many zi's. Okay. So the final solution of this problem was not given by Bohr, of course. It was solved much later in 1931 by Born and Bustenhude. So they actually showed that the width of the strip is actually half. So, but I mean, during this course of investigation, what became clear to Bohr that the power series infinitely many variables that has to be studied in more details to, to handle this problem successfully. So basically, that led him to continue his investigation on power series. He started with power series of one variable, and that gave his this notable theorem in 1914, which says precisely if fz is a complex valued analytic self-map of the open unit disk D with this Taylor expansion sum over n0 to infinity anz power n, then the majorant series given by sum over n0 to infinity mod n r power n less or equal to 1 inside the range mod z less or equal to 1/3. And this quantity 1/3, it cannot be improved. So that can be seen by considering disk automorphisms and calculating the radius, of course. So Bohr initially obtained that result for mod z less or equal to 1/6, and that was later sharpened to mod z less or equal to 1/3 independently by three mathematicians, Wiener, Riesz, and Schur. So basically, after 1914, for a long time, this is a surprising result, of course, but it is not received much attention. In 1995, a connection with the theory of operator algebra was discovered. So basically, it was known for a long time that operator algebra satisfy the von Neumann inequality. But is the converse true? So that was a long-standing question, and in 1995, Dickson, he used this Bohr's theorem to construct a commutative Banach algebra that satisfies the non-unital von Neumann inequality, but is not an operator algebra. So the question was answered in negative by him. So, I mean, I have noted down that particular algebra that he considered, that was precisely the algebra of summable complex sequences with convolution multiplication, as we know, but with a different norm. He multiplied the usual norm, the one norm by 1 by beta. So it can be shown that for beta belonging to open zero closed one interval, this new algebra A beta that is not isomorphic to an operator algebra, but using Bohr's theorem, it can be shown that if beta belongs to 0, 1/3, this interval, then A beta is going to satisfy the von Neumann inequality. So after this application was discovered, So many mathematicians started studying this Bode inequality in many different settings. So in particular, I mean, there are several different directions in which this inequality was extended, but in particular, we will concentrate on complex valued and operator valued functions and some developments on it. Okay. So one of the subsequent developments that was done on Bode's theorem, that is theorem by Bomberi in 1962. So what he proved, he obtained Bode radius in terms of the initial coefficient of the Taylor series. That if we are given fz as lambda plus sum over n1 to infinity n z power n, which is a holomorphic self-mapping of D, then the Bode inequality given by this lambda plus sum over n1 to infinity mod a n r power n less or equal to 1. This one is going to be satisfied for mod z less or equal to 1 divided by 1 plus 2 lambda, while lambda is bigger or equal to half, and otherwise it is satisfied for mod z less or equal to square root of 1 minus lambda by 2. And again, by considering these automorphisms, one can see that for lambda bigger than half, this radius 1 divided by 1 plus 2 lambda is the best possible. So this is a quite classical result, but interestingly, the best possible value for this Bode radius for lambda less than half in this theorem, this is still unknown. And it is believed that many new techniques are needed to handle that problem. Okay, so as a consequence of this theorem or the techniques that was used to prove this theorem, one can also get this important result that if we have a complex valued holomorphic self-mapping of the open unit test D, then the majorant series, the growth of the majorant series is controlled by the quantity 3 minus square root of 8 into 1 minus r square divided by r inside the range mod z belonging to closed interval 1/3 and 1 by square root of 2. And this bound that we have here, this is optimal. So, I mean, the importance is actually this is giving the growth of the majorant series beyond 1/3 and up to 1 by square root of 2. Again, for r bigger than 1 by square root of 2, the exact quantity that should replace this right-hand term, this term in the right-hand side, that is still unknown. So what we have done, we have considered some operator valued analogs of Bode's theorem, Bomberi's theorem and its corollaries. So we have taken operator valued holomorphic functions, functions which map D inside BH, the space of bounded linear operators, with the Taylor expansion sum over n0 to infinity nz power n, and with some additional assumptions. While a naught, the first operator coefficient is a normal operator, and this commutes with every other coefficient. Now, if we assume that norm of f is less than 1 for all z, then this operator inequality, sum over n0 to infinity mod an, absolute value of the operator, into r power n less or equal to the identity for Ri less or equal to I plus 2 mod a naught whole inverse, while we assume mod a naught is bigger or equal to I by 2. And otherwise, this is true for Ri less or equal to half into 1 minus mod a naught whole power square root of the whole operator. So using, I have included a brief outline of the proof. So basically what lies in the heart of this proof is the Fourier-de-Putnam theorem. Using it appropriately and repeatedly, so one can construct automorphism type thing given by this phi fz minus a naught into 1 minus a naught star into fz whole inverse. So that is going to be a holomorphic function from D to BH with norm less than 1 and fixing the origin. So from this, one can obtain a representation of fz, and then we get certain inequalities on the coefficients of f, like this square sum of the coefficients up to a certain k, and then we use some Cauchy-Schwarz type inequality to estimate this quantity n1 to k sum over n1 to k mod a naught power n, and then we need to use a summation by parts to get a proper estimate on the quantity sum over n1 to k mod a n r power n. So, and now using this and with some calculations, we will arrive the first conclusion of us, and the rest that will basically follow from the an analog of the Cauchy-Schwarz inequality, basically like that sum over n1 to infinity mod a n r power n less or equal to I minus mod a naught square root of half r divided by square root of 1 minus r square. This is for the second part. Okay, so uh, under the hypothesis, so what we have assumed in the statement of this theorem we just stated. So if we assume the same hypothesis, we will get an analog of Bohr's inequality in operator valued settings, that this this majorant series type thing, sum over n0 to infinity mod a n r power n. This is again less or equal to the identity operator inside the range mod z less or equal to 1/3. Okay, and another corollary that is also an operator valued analog of the corollary by Bomberi. If we take operator valued holomorphic function with one additional assumption that the initial operator coefficient is basically a scalar operator. That means scalar, a complex number multiplied by the identity, and the rest of the series remains the same. So it basically satisfies all the hypotheses of the theorem we stated. Then the growth of this thing, mod n naught I, n1 to infinity mod a n r power n, that is controlled by this quantity 3 minus square root of r in 8 into 1 minus r square by r into identity inside the same range mod z bigger or equal to 1/3 and less or equal to 1 by square root of 2. Okay, so that was one part of our discussion, and then we are going to discuss some extensions in the complex value situations in particular. So the Bohr inequality, basically we can reformulate it. So if we take that mod a naught term, take that mod a naught in the right hand side of the inequality. So it now looks like sum over n1 to infinity mod a n r power n less or equal to 1 minus mod a naught. Now 1 minus mod a naught is precisely the Euclidean distance between a naught and the boundary of the unit disk. Okay. Now, one natural question is, I mean, can one give a proper form of the Bohr inequality in for functions that map D not inside D, but inside some other domain omega? Then in this definition, in this one, inequality one, we can just replace this open unit disk D by omega, and that definition will still make sense. So in this case, the existence of an R naught belonging to 0, 1, for which the inequality sum over n1 to infinity mod a n r power n less or equal to Euclidean distance between f0 and the boundary of omega holds for all mod z less or equal to r naught, will be said to be the occurrence of the Bohr phenomenon for functions which map D inside some general domain omega, which is not necessarily D. So with that definition in hand, in 2010, Abu Muhanna showed that the inequality 2, this one, this Bohr inequality remains valid for mod z less or equal to 3 minus 2 root 2 if we assume that omega is only simply connected, and this quantity 3 minus 2 into square root of 2 that can be improved to 1/3 if omega is convex. So most of these constants, those are the best possible. So those can be seen by taking wave functions and half plane mappings. Okay. So what we want to consider several variable extension for these definitions. So precisely what we are going to use the polydisk, the open unit polydisk, while the sup norm of the quantity z given by this n tuple z1, z2, zn, sup norm of this z is less than 1. And we know that any holomorphic f going from polydisk f that maps the open unit polydisk inside the complex plane, that can be expanded in the power series given by this equation 3. We write it using the standard multi-index notation. Okay, so we need a notion of the Bohr phenomenon that can be extended in several ways. So we are particularly taking the approach of Bose and Kavinson, which was, I mean, the pioneering work in this direction. So basically that states that we will denote by Kn the supremum of all R belongs to 0, 1 such that this inequality, this is the Bohr inequality in the several variable situation, what we will consider. This inequality holds for all Z inside the polydisk that satisfies subnorm of Z less or equal to R, and for all holomorphic F that maps the open unit polydisk inside the open unit disk in the complex plane. So using that definition, this kind of work began in 1997. So, I mean, there has been a lot of work, but again, interesting thing is for any n bigger than 1, the exact value of Kn in terms of n, it has not been determined yet. So the first result was this one, that Kn is bounded below by 1 divided by 3 into square root of n and bounded above by 2 into square root of log n by square root of n. Okay. So the best result actually what is known in this direction so far. So that is given by Frederick Baird and 2 other mathematicians in 2014 that states that Kn behaves asymptotically as square root of log n by square root of n as it tends to infinity. Okay. So what we thought of doing to extend this kind of results in for functions that are defined on polydisk but do not map inside D but on rather general domain. So we denote by Kn omega analogously the definition of Kn. Kn omega, the supremum of all R belongs to 0, 1 such that this Bohr inequality sum over K1 to infinity and sum over mod alpha equals K mod C alpha Z for alpha, that is less or equal to Euclidean distance between F0 and the boundary of omega. For all Z belongs to N that satisfy subnorm of Z less or equal to R and satisfied for all holomorphic F that maps the polydisk inside some domain omega. So, and we further define one more quantity that is given by this Kn tilde, that is the infimum over Kn infimum over omega, such that omega is simply connected taken on this quantity is Kn omega. And according to our notation, we easily see that Kn is basically Kn of D, according to our notation. So what we have been able to prove that this Kn tilde, this quantity is also behaves asymptotically as square root of log n by square root of n as n tends to infinity. So basically the key, I mean, the thing that is at the heart of this proof is the Bohnen-Stille inequality. This is given by this inequality 4. So this kind of inequality, I mean, it was known that the quantity on the left-hand side is bounded by C into this soup thing actually, that was known, but I mean that constant C that can be written as C power m type things. So that was the hypercontractivity of Bohnen-Stille inequality that was proved much later in 2011 only. And then Baird and the other mathematicians, they improved it to this form, which I have written here. So using that inequality and for this supremum soup associated thing, soup of norm Z infinity equals 1 mod of this whole thing, sum over mod alpha equals K alpha Z power alpha. This part has to be estimated. This estimate, we can achieve this from, I mean, some function theoretic techniques. We can say that this is less or equal to 4K into df0 del omega. Okay. And then we need to use some analysis, which is kind of complicated, but can be done. So, and then further generalize as a further generalization. So we consider functions that are defined on some domain on Banach space and takes values in the complex plane. So basically, let X be a complex Banach space and G inside X and omega inside C are two domains. For any holomorphic mapping F that maps G inside omega, we will denote by dkfx the kth Frechet derivative, and we know that any such F can be expanded into the power series using this Frechet derivative like this. Fx equals sum over k0 to infinity 1 by k factorial dk f x naught x minus x naught whole power k, like this equality 5. So using this notation, we give an analog of Bohr's inequality for this kind of functions. And the corresponding Bohr radius is precisely given by kxg of omega for a specific domain omega. And the Bohr inequality, the analog of Bohr inequality is given by this inequality 6. And again, like we defined kn tilde, we define kx tilde g, which is simply the infimum of kxg omega, while omega is simply connected, and kx double tilde g, which is again the infimum of kxg, while omega is convex. So what we proved using these concepts, that kx tilde g is again going to be 3 minus 2 into square root of 2, like the scalar valued case, and kx double tilde g was 1/3. Okay, so after all this, so I would like to finish with some points. I mean, what problems can be attempted in future based on this discussion. So one can try to extend the theorem of Bombedi for lambda less than half with the best possible radius. So that was, I mean, open since 1962, as we have stated. So, and also one can try to find analogs of Bombedi's theorem in other vector valued situations, like the functions that are defined on a domain in a Banach space X and that take values inside another Banach space Y, or for the complex valued functions defined on the poly-disk or the unit ball of LP spaces. I mean, all kind of abstract situations maybe. And then establishing an operator valued analog of Bombedi's theorem with minimal assumptions on the function's coefficients, because I mean, the theorem we proved, it actually assumed that the initial coefficient is normal and that coefficient, initial coefficient that commutes with every other coefficient. So can one further realize these assumptions? So again, then coming to the Bohr radius for in several variable situations, finding the exact value of kn for any n bigger or equal to 2, that's a problem since 1997. So similar problem can also be attempted for kn tilde. And then one can study quantities similar to kx tilde g, while I mean we have taken as the codomain as the complex plane. So one can take spaces while the dimension is bigger than 1 and can study quantities similar to kx tilde g. Okay, finally, I mean, if one only considers functions that are defined on D and take values inside the complex plane only, there are still many problems that are, I mean, quite difficult to handle. Like, I mean, for function classes, I mean, Bohr phenomenon can be investigated for function classes, while the optimal coefficient estimates for those classes are unknown. Like, if one tries for hyperbolically convex functions or harmonic univalent functions, those are some problems that are worth attempting. Okay, so I mean, I would like to finish with this. Thank you for your attention.
An audience. Thank you, Nina.
Thank you.